The River Elbe in Stade. Hundreds of ships provide a gigantic flow of goods toward Hamburg harbor. A force that keeps the German economy afloat. The Procon Nord Industrial Park in Stade. Here, too, mass flows are moving forward. The technologies used here not only keep today's economy running, they also lay the groundwork for the future. On the site of a former aluminum plant, ethanol and wind turbine components are produced in a way that conserves resources. Most of the energy used here comes from waste. In a backup thermal power station, energy-rich waste is collected in a bunker. The waste is made up of carpet and clothing remnants and industrial packaging that cannot be recycled or stored in a landfill. With the help of a mechanical grabber, workers mix the waste and carry it to the opening of a furnace. Inside the stoker-fired furnace, the energy stored in the waste is released at temperatures of more than 1,000 degrees Celsius. The lost heat produces steam that engineers in Stade use to produce electricity. They also apply the steam to industrial processes in the neighboring facilities. The connection of power production and industry is optimal, since steam is a constant source of energy for manufacturing. That dramatically increases the efficiency of the power plant. One important energy consumer is the Stade ethanol plant. Every year, nearly 300,000 tons of wheat are fermented into alcohol here. The organic fuel is then added to gasoline in refineries. To ensure the fuel's positive energy balance, ethanol has to contain substantially more energy than is needed for its production. Each step of the production process is especially designed to reach this goal. After it's ground, the flour is then sifted through a fine sieve. The rougher husk of the grain, known as bran, is extracted since it cannot be fermented into alcohol. The Stade ethanol producers market the bran in the feed and commercial food industry. Along with financial benefits, there's an energy benefit too. After the bran is delivered to its new destination by truck or rail, it no longer needs to be heated in further processing, such as sweetening or fermentation. That saves energy. Following the sifting process, the flour is mixed with water. It still contains starch and gluten. But the protein-rich gluten is also incapable of fermentation. The watery mixture flows into a centrifuge in order to separate the two substances. The rotational power presses the heavier gluten outwards. A special spiral carries the gluten to the right, while the starch mixed with water flows to the left. That's how the two substances are separated. The moist gluten slides over a special sieve, filtering out even more starch-laden liquid. The northern German engineers have another use for gluten, packing the dry, protein-rich substance in large sacks. Just like bran, they can now sell gluten as animal feed or market it in the food industry. Aside from the additional income, separating gluten and bran creates other benefits as well. Only the filtered starch flows into the sweetening process. In large containers, the starch is liquefied at temperatures of more than 90 degrees Celsius and converted into glucose. Due to the filtering process, only about 2/3 of the mass flow needs to be heated, saving a large amount of energy. The glucose that results from the sweetening process is fermented into alcohol with the help of yeast. And because the fermentation takes place without unwanted impurities, the resulting alcoholic product is relatively clean. That allows the technicians to extract the yeast from the alcohol-containing feed in a special separator. The separator forces the heavier yeast to the outside. The alcoholic portion is drawn out of the middle and flows into distillation. The efficient management of mass flows means the yeast is once again used for fermentation in a recycling process. And since the gluten and bran were already separated in the centrifuge and sifter, some 1/3 of the heat is conserved in the energy-intensive sweetening process. Along with these procedures, the Stade ethanol producers use further energy-efficient technologies. Between each step in the process, substances flow through heat exchangers that win back a part of the process heat. Directly before fermentation, the glucose dissolved in water flows through several pipes. It comes from the sweetening and still has a temperature of more than 60 degrees Celsius. In the heat exchanger, the glucose transfers part of its heat to the starch, which must be heated before it flows to the sweetening. The cooled-off glucose flows into the fermenter, where it's processed at around 30 degrees Celsius. The fermented feed then flows into distillation. In the center of the distillation column, the alcoholic feed flows out of the fermenter over several layers toward the bottom. That's where steam rises in the counterflow. The flow extracts alcohol from the feed. The water portion condensates on the upper plates, concentrating alcohol in the steam. Thermal energy from the steam is also captured with the help of a special vapor compressor and dedicated heat exchanger.
We use up to 50% less energy in our ethanol production process than other European manufacturing processes. We consider this an optimal use of energy and a good basis for sustainable production here at our site. We don't need to import raw materials from regions outside of Europe, and that is a huge advantage for sustainability.
Und das ist ja nochmal ein deutlicher Vorteil für Nachhaltigkeit.
Every year, the ethanol plant produces 100 million liters of biofuel made from domestic wheat. The alcohol is shipped to refineries by rail or truck. There, it's added to gasoline in order to conserve fossil fuels. 7 refineries are enough to produce the entire amount of ethanol called for by lawmakers in Germany. The manufacturers use the waste heat of a nearby power plant, managing mass and energy flows in an extremely efficient production process. Ethanol production in Stade reduces CO2 emissions by 50% compared to conventionally produced biofuels. And thanks to the marketing of byproducts, the plant is able to improve its overall cost effectiveness. The location, however, is also home to other companies that use the nearby solid recovered fuel plant. One part of the steam produced here flows into the neighboring iron foundry. Here, workers are making a mold for the hub of a wind turbine. They spread casting sand around a wood positive. Global demand outstrips the supply of large molded components for wind turbines. Making them requires both large molds as well as large ovens. The foundry in Stade possesses the world's biggest ferrous ovens. And most of the electricity they need comes from the neighboring power plant that obtains its energy from waste. The workers pull out a special boiler with iron heated to more than 1,300 degrees Celsius for deslagging. Before the actual casting, workers have to remove impurities from the surface of the molten metal. Afterwards, the boiler floats to the cast. Using special sensors, workers measure the temperature of the molten mass. To ensure a high-quality wind turbine hub, the casting process must be done carefully, but also as quickly as possible. After the casting, it's important that the component doesn't dry too quickly. But since the hall is heated by steam from the power plant, that's not a problem. In Stade, large wind turbine components are manufactured right next to the ethanol plant. And one more company here takes advantage of the available clean energy streams. In the former electrolysis hall of the aluminum plant, more than 100 workers now assemble the blades for 5-megawatt offshore wind turbines. And since the blades are 60 meters in length, the long hall is an ideal production site. Plastic resin and adhesives are used for the assembly process. For the optimal use of these materials, workers need constant room temperatures. In the winter, that's provided by a 400-meter-long heated floor. The hot water is provided by the neighboring power plant. Once the upper and lower blade shells are finished, the two parts are then joined together. Rapid growth is expected in the wind energy sector, and that places even more importance on the conservation of resources used for the production of wind turbines. At the Procon North industrial site in Stade, companies that produce wind turbines and biofuels are also creating important components for the era of renewable energy. That includes the use of energy from waste and a highly efficient mass flow management. Just a few meters from the River Elbe, a model 21st century industrial site has taken shape. And that could keep the goods flowing through Germany for a long time to come.